tips. I might actually add to that list of problems, just, you've got the ones you have to turn in. I might maybe throw in a couple more if I think of other interesting things. Actually, another thing I posted, I don't know if you guys noticed on the website, I've got a few, applications of some of this stuff. So on Tuesday, I'm hoping to maybe just say a little bit about, why would you care about these various, even, odd permutations, things like this, and I posted a couple links to some, I think, cute applications, but maybe I'll talk about one or two of them on Tuesday. So, questions about anything, you guys? So we're missing people. I think there's some you teach going on. I had a few people who had official documents. Okay, so that's for later. Okay, so you guys do have a worksheet today. So maybe we're going to actually change gears. We're going to talk about chapter 10 today, but let me just recap chapter 9. So actually just recap of chapters, I guess this is actually like almost 6 through 8, at least 7 and 8. So just to kind of close the door on those topics for now. So I mean, the idea here was we were studying the symmetric group. Right, well, SA, which is really the set of all permutations of a set A, so the set of all bijections A to A, and in particular, right, Sn, this was the set of permutations from 1 through n to itself, right? And we looked at, well, we wanted to understand this group, and well, first of all, we looked at various examples of this guy. We saw the dihedral group kind of sits in here. The symmetries of a square sat inside S4, and so this is sort of a rich structure that encapsulates a lot of things we like. But we looked at the sort of structure of elements, an element alpha in Sn. So let me just remind you guys that first of all, our main kind of observation was that there's a canonical or well-defined factorization. So first of all, alpha, is can be uniquely written. So uniquely is always this little caveat here because it's really up to reordering as a disjoint product of cycles. Right, so you have that little algorithm that tells you sort of how to do it, right? It's just look at one and see where it goes and close off the cycle and then take the next smallest guy. Remember this whole thing? So that's kind of the nice way to represent the element alpha. But then we wanted to say, well, can you actually break it up further into these two cycles? And the answer is yes. So you sort of can break it up further. Also, alpha can be written not uniquely anymore and not disjoint anymore, but as a product of transpositions. Well, so I'll just use words here. Product of transpositions. So transposition is just a fancy word for a two-cycle. And just, again, the warning here is it's not unique. So this is not, okay, so of course this is not a disjoint product anymore. These transpositions are overlapping in general, right? You have 4, 5 times 6, 5 maybe. So this is not, and also not unique. Not unique factorization. Right? But what is unique is the parity, right? So if you write it out as a product of transpositions, it's always either an even number of them or an odd number. So the parity of the number of transpositions is unique. Is well-defined or is unique is, I'll just say, it's always the same. And that's what gets us into this notion of odd or even permutation. Okay, so that's just kind of a recap. I just wanted to, we kind of rushed at the end there. So in your worksheet today, you'll play around a little bit with these guys. Questions about this theory? So this is kind of the basics of symmetric group theory, the sort of how you deal with elements. And we'll keep playing with this group as we go along, but this is the sort of basic language I want to use to talk about these. Okay? And again, I don't know if I convinced you guys or not, but transpositions are just two cycles. So these are the sort of easiest things you could hope for to understand a permutation, is these local moves that just switch two things. And like I said, Tuesday I'll try to talk about kind of a cute application. Okay, so I want to get to chapter 10 now. No questions?
I got a quick one.
Okay, good.
You've been saying a disjoint product of cycles. Is that the same thing as a product of disjoint cycles? That's more of a just notation thing. I was just curious.
Is that what I should say?
I
Yeah, I think
don't know
you're
if
right.
there's a
That matters, right, where that adjective goes. Disjoint product, does that not make sense? I mean, you know what I mean, right?
Yeah, I know what you mean. I was just curious
right.
if those mean the same thing.
I guess you're right. It's a product of disjoint cycles, right? Because the cycles are the things that, okay, good. But that's not the same. I don't know what a disjoint product would be.
I assumed it meant the same.
I think we use that. I mean, I think those are synonymous, but let's, yeah.
Okay.
Okay. Yeah, I think those are the same words, but you know what I mean, right? So the cycles don't have anything in common. You talk about disjoint zone, right? Something like that. Okay, good. All right, let's go to chapter 10. So this is actually a short chapter, but I think just kind of an important notion to have in mind that I want to include on this first exam. So this is called the order of an element. Chapter 10 is about the order. So we're leaving symmetric groups now. We're going to talk about general groups, okay? So order of an element is the title of this chapter. So let me just start with let's warm up a little bit before we give you the definition, but just let me set the stage here. So let's let G be a group. So just any group now, right? So again, we're not just talking about symmetric groups. It could be anything, the integers or Z5 or dihedral group, whatever. Let's let A be an element of G, and just recall some notation. The notation that we were using here is that A to the N, let me just make sure we know what that is, right? So A to the N means that I'm taking the group operation N times, and we've seen this before, but I just want to make sure we're on the same page. And then A to the minus N, right, of course, is you take the inverse of A and you multiply it by itself N times, right? So again, something we've seen a lot, but so I'm using what's called the multiplicative notation for a group. And then of course, what's A to the 0? I mean, our convention is A to the 0 is the identity, right? So you can think of it as A to the 1 times A to the minus 1. Right? So A times its inverse is the identity. So these are just some notation we've been using, but I want to make sure we're comfortable with them. And just one more comment. Also, the laws of exponents, I guess you call it in calculus class, hold in an arbitrary group G. What I mean by that is, e.g., if I take A to the m times A to the n, that's A to the m plus n, right? We've seen this before, but I just want to, I'll say et cetera. So. Okay, so I think we're comfortable with that stuff. I just want to put it on the board. So here's a definition. So suppose G is a group. And A is an element. Okay. So the order of A, of the element A, is the smallest positive integer let's say, I'll use his notation, n, such that A to the n equals E. And I should say, if it exists. So if there is a positive integer, we say, in this case, we say that A has order n. So A has order n. And if no integer exists, so we'll talk about this in a second, we'll parse this. All right, so what I'm doing here is I'm just taking powers of A, and I want to know, do I ever get to the identity? The smallest number that I have to, the number of times I have to apply the operation to get to the identity is called the order. We say that A has order n. Sometimes I'll write O of A equals n. That's sometimes a notation. I'll try to avoid that because it gets confusing sometimes, but you might see it here and there. And then, it could be the case that no such integer exists, in which case, so if no such n exists, if you can never get to the identity, we say that A has infinite order. Okay, so let's play around with this a little bit. Yeah, so again, order. I should actually give you guys a warning. There's a sort of unfortunate coincidence of notation here that, let me just say it here. This is different than the order of a group. So we've talked about in this class, and maybe seen in the book, let me just say note here, a warning, the order of G so sometimes written just bracket G, or sorry, bar G, absolute value bar G. That's just the number of elements in G. So this is a different notion. So this is about the order of an element, right? It has this meaning that you take the powers of A and C when you get to the identity. The order of a group, which is something I might have mentioned, that you've seen in the book, is just the number of elements. So this is a much more basic concept. This is just the cardinality of the set, right? The order of the group. Well, this is a more kind of, well, I think maybe new definition. It's this thing about taking powers. Okay, so you got the order of a group, you got the order of an element. Those are, we'll see later that they're related. But for now, let's just think of them as two different things. Okay, so let's talk about elements of, I don't know, let's do S3. Okay, so what's S3? Let's use our fancy notation of cycle notation, right? So what do we got here? So I'm not going to write this as permutations 1, 2, 3 to 1, 2, 3. I'm going to use our cycle notation because it's a lot more efficient. I've got the identity. What else do I have? Well, I have these little transpositions themselves. So how many of those are there? I've got a 1, 2. Right, that's the thing that's a permutation that just switches 1 and 2 and leaves 3 alone. What are the other two transpositions? 1, 3 and 2, 3. And then I've got some 3 cycles, right? That would be the other kind of element that sends 1 to something, a 3 cycle, a little triangle. So what's the first kind? I can send 1 to 2, which then has to go to 3, which goes to 1. And then I claim there's only one other 3 cycle. It would be the inverse of this guy. 1, 3, 2, right? And again, these cycles are only defined up to this circular cyclic order on this, right? So this would be the same as 2, 3, 1. Okay, so you guys good with this notation? Those are the elements of S3. What are the orders? Well, okay, so I just said I'm going to avoid that O notation, but here it is. So what's the order of the identity? That one's always easy, right? How many times do I have to take the identity times itself to get the identity? Actually, that's a good question. I think we're going to call this order 1, though, right? So, actually, I thought that was an easy one, but what is our convention here? I have to take it, right? So I want to say that's order 1. And that's the only element that's going to have order 1, right? It's how many times do I have to take the element to get the identity? Well, if I take it just once, then it is the identity, right? A to the 1 equals E means that A equals E. Okay, what about the order of 1, 2? Well, let's look at it. So, I've got Well, 1, 2 to the first power is 1, 2. 1, 2 squared is 1, 2 times 1, 2, which equals the identity. And that's the smallest, so that's the smallest power I can take to get to the identity. So what's its order? 2. So the order of 1, 2 is 2. Well, this is actually your first question on the worksheet. I'm going to give you guys a, in general, if you have an R cycle, can you see what the order will be? I was going to have you guys think about this on your worksheet, but what's the order of 1, 2, 3? So maybe we'll work this. Let's work this one out explicitly. I think you'll see that. So again, if you want to know the order of an element, you start taking powers, and you see when do I get to that identity. So let's see, 1, 2, 3 to the first power, of course, is 1, 2, 3. Not the identity. 1, 2, 3 squared is, well, that's 1, 2, 3 times 1, 2, 3. What is that? So let's see, are we comfortable with our symmetric group arithmetic here? So 1 goes to 2, which goes to 3. 3 goes to 1, which goes to 2. 2 goes to 3, which then goes to 1. So it's this guy. That's the inverse, of course, of that guy. So not the identity still. What happens when I take 1, 2, 3? Well, that's 1, 2, 3 times 1, 2, 3 squared, which was 1, 2, 3 times 1, 3, 2, which we just did. And, well, what is that? I claim that this was the inverse of this guy, so we know what it is, but let's go through the calculation. 1 goes to 3, which goes to 1. 2 goes to 1, which goes to 2. And 3 is fixed as well. So that's the identity. So what's the order of 1, 2, 3? 3. Okay, so this implies that the order of 1, 2, 3, 3. That's it. That's order. Okay, so it's not, I don't think it's too much to digest. We're going to now, actually, let me point out one thing here. So let me note something here. If I take the element 1, 3 and I raise it to the 4th power, that's 1, 3, 1, 3, 1, 3, 1, 3. That's the identity. You can trust me on that. If I switch 1, 3, 1, 3, 1, 3, 4 times, that's the identity. So can I say the order is 4? Okay. Right, so what did I miss here? It's the smallest, right? So it's not just that the power, so when you guys are checking that something has an order, it's not just that the power is the identity, it's got to be the smallest guy. Okay, so that's a common mistake, that people forget to check that it's the smallest thing, right? Just because, so checking order means that it is the identity when you take it to that power, and that no smaller thing is the identity, no smaller power. Okay, so I'll say, but order of 1, 3 is 2. Okay, let's do one more example of a group. So what's your other favorite example of, so again, when I pass out your review sheet here, one thing I want you guys to always have in, when you're working on groups in general, you should always have examples in mind. So what's another group we know that has 6 elements? You guys know another one? Z2 cross Z3, that is one. Actually, Z2 cross Z2 cross Z2 is another one. I had an even simpler one in mind, maybe Z6. Right, that has 6 elements. So what about elements in Z6? Maybe I can even say now that there's a strong sense in which Z6 is actually the same group as Z2 cross Z3. We're going to get to that after the exam, but for now, Z6. So Z6 with addition, right, that's going to be, what is that? 0, 1, 2, 3, 4, 5. Okay, well, I think that you guys are seeing what this is. So what's the order of, say, 2? Well, again, 2 to the first power. So again, there's this kind of annoying well, confusing notation. That I'm using the multiplicative notation for the group, even though addition is the operation. So 2 to the 1 is really, well, it's 2. What's 2 squared? Well, so far we're okay. This is 2 plus 2, which is 4. 2 cubed is 2 plus 2 plus 2, which is, well, not in this group, right? Right, that's 0. And what is 0? That's the identity. So this implies the order of 2 is 3. Maybe one more. What's the order of 5? Well, you know, oh, maybe I'll let you think about that. Anyone know what it is? It's 6, right? In fact, if you take anything relatively prime to that number here, it'll be, and so you can maybe see the pattern that's developing here. You know, 2, you know, was not relatively prime to 6. In fact, if you divide 6 by 2, you get 3. Well, so there's some basic number theory going on here, right? So, yeah, let's maybe do, okay. No, I'll let you ponder that. I think you've got a homework problem that's similar to this, so I won't give it away. Oh, and so I wanted to, one example of what I was just erasing here, what about elements of infinite order? Right, I was just, so what about now elements of Z? So, I don't know, what's the order of 2 now? Well, you know, I mean, we can try to play this game. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is now 6, 2 to the 4 is now 8, and I'm not going to get to 0 anytime soon, right? So this is never going to go to 0. So the 2 has infinite order. So this is dot, dot, dot. This implies that 2 has infinite order. In fact, every element of the integers except 0, right? So every element, every non-zero element of Z has infinite order. Okay. Okay, so let's prove a couple of facts about orders, and this is the basic idea. So I guess the formula here is going to be, right, if I'm in Zn, and I want to know the order of M, I take the GCD of M and N, and then take N divided by that. That would be the, but I'll let you maybe come up with a formula. Yeah, what's the order of an element in Zn? I'll let you think about it. I have to write down any formula. Okay, so let's prove some facts about this guy. So I should say that when we're, you know, you already see that when we're talking about order, some basic number theory is always going to be in the background. And actually one thing you want to always, you know, one useful tool in this context is division algorithm of integers, right? So the division algorithm. So you guys know this from your, well, maybe from junior high, but maybe also in your number theory class. So if M and N are integers, and let's just say, let's take N to be positive. I don't want to divide by 0. Then there exists a unique, you know, I can divide, I guess, M by N, right? And I have a quotient and a remainder. So then there exists a unique, I guess we call them Q and R, such that, see, I'm dividing M by N. So M equals NQ plus R. And of course, the remainder should be small. So this is where 0 is less than R is strictly less than what I'm dividing by. All right, you guys know this one. If I divide 7 by 3, I can write 7 as 3 times 2 plus 1. Okay, so this is going to be useful when we're talking about this stuff. Let me show you an example of where you can apply this. So just give you a basic, what did I say? E.g. if m equals 7, n equals 2, then we know that 7 equals 2 times 3 plus 1. Okay, so here's the theorem. We got, I think, 3 theorems. I'm going to have you prove one in homework. So if the order of an element A is n, then, so this is kind of a useful fact, if the order of an element is n, then it actually happens that the first n minus 1 powers of that element are different. Okay, so then there are exactly n minus 1 distinct powers of A given by, well, I'll have a to the 1, which is A. No, so actually I want n distinct powers, of course, right? So a to the 1 is A squared, A cubed, up to a to the n, which is what? If n is the order, what is a to the n? This is the identity. What I'm claiming is that all of these are different. Okay, so proof. I got to prove 2 things here. So I'm saying that there's exactly n and there's no others. And so I'm saying that there's n powers given by these and that every other power is one of these. Okay? So suppose you give me, well, let's consider just a to the m for any m integer m. So I claim that it's actually one of these in the list. We claim that a to the m equals a to the I for some, 1 less than I less than n. So it's actually already in this list that I've given you. You gave me a to the 6 million. I claim it's actually one of these. Okay, well, how do you do that? Well, I'm going to divide m by n. So use the division algorithm to write, let's see, so I want to write, okay, good, I got my my letters matched up here. So this is, m is going to be nq plus r, right, for 0, okay.
But isn't m less than n?
It could be, in which case what's n going to be? Or sorry, what's q going to be? I mean, m is arbitrary. Am I missing something? So the order of A is n, and now you've given me just an arbitrary integer m, and you took a to that power. So let's say that A had order 5. So I've got a squared up to a to the 5th, and then you give me a to the 6 million, or you give me a to the minus 2, or you give me a to the, you can give me anything. I claim that whatever you give me is actually equal to one of these things. That's what I'm trying to prove. So m can be anything. It can be smaller than n. Then it's going to be easy to show that it's one of these, right? It's actually already written as one of those. So what I'm trying to show is that you give me a to the m for any power, and it's actually already it's equal to one of these.
Oh, okay.
That's what I'm trying to show, that this actually captures all of the powers.
I
make
thought that m had equal I, and that's not true. That's
Oh
what
no,
confused.
for I, yeah, so I'm claiming that it'll actually equal a small power of a that I've written down,
Okay.
right? Okay, so let's see. So we've got m written as this, quotient times n plus remainder. So if we take a to the m, that's the same as a to the nq plus r, and here's where we use our magic of the laws of exponents. So this is a common trick. What's a to the something plus something, right? So again, in calculus class, you learn that this is a to the nq times a to the r. I mean, it's the same laws of exponents here. And again, let's use some laws of exponents to write a to the n times q is the same as a to the n to the q. Right? That's a law of exponent that we learned in calculus. Times a to the r. But what's a to the n? The identity, right? Because the order of a is n. So this is the identity to the q times a to the r. Right, what's a to the q? Well, e to the q is always, well, the identity to any power is the identity, so this is a to the r. Yeah, so, and that's what we wanted, right? So this is a little bit annoying, I switched notation a little bit here. But since a to the n is 0, right, this is the same, and this is what we wanted, right? So, I mean, the convention is to write your remainder like this, but since we're in this group where a to the n is actually the identity, this is what we wanted. So this is as desired. All right, so we actually wrote the thing you gave me as a to a small power, one of the in the list. So if you like, I could write this as a to the 0, and write this as a to the n minus 1, and then it really does match here. Okay. You don't have to change your notes because everything's cool, but if you want it to really match the convention here. Okay, what's the other thing I need to check is that these are actually not redundant at all. Right, so we've shown that if you give me any power of a, it's one of these. But what if I listed something twice here? So next we want to show, we claim that if, if we take anything, so now I've kind of changed so that was kind of a bad idea, right? So sorry, I'm going to go back to, so this is dot 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 a to the n, which is e. So next I claim that if I take any two of these elements, they're not the same. So if, let's say 1 is less than I is less than n, and j is less than I is less than n, then, a to the I equals a to the j implies that I equals j. Okay? Well, how do you prove this? So to prove this, well, let's suppose not. Let's say that I is bigger than j, right? So if they're not equal, one of them is bigger. Well, then we can divide by, or we can multiply by a to the minus j on both sides. Multiply by a to the minus j above. And what do you get? And remember to bring chalk. Okay, so if I take this equation here and hit it with a to the minus j, I get a to the I minus j equals a to the j minus j, which is what? What's a to the j minus j? Identity. But look at this now, I've got a to the I minus j equals the identity, and I and j are both less than n and bigger than or equal to 1. So that implies that I minus j is less than, it's a positive number because we assume that I is bigger than j, and it's smaller than n. So this is with I minus j less than n. If I take two numbers between 1 and n and subtract them, they're in absolute value, they're going to be less than n. Since it's positive, it's actually less than. So what's the problem? What does that contradict?
That would mean the order was less than n.
Right, so the order, that's a contradiction. The order of a is n, so that's the smallest power. We just cooked up a smaller power that was the identity. This is a contradiction to the order of a equals n. And hence we got what we wanted. Okay. So I equals j as planned. Okay, so then again, the punchline of all this is that if you've got order of A equals n, these are all different powers, and then those are the only thing you get by taking powers of A. That's a useful fact, okay, so we're going to use that a lot, actually. Okay, so questions about that one? I think that'll be my sort of last proof of the day. I'll write down a couple more theorems and then we'll take a break. So questions about this argument, was that clear? This is sort of how you got one on your homework that's kind of similar to this argument. I mean, using the division algorithm, that's kind of a typical thing. Well, let me say one thing here. So another theorem is useful for us. What if we're in the context of infinite order and we look at the powers of A? So the theorem is if the order of A is infinity, then what happens when I take powers of A? How many different ones will I get now? Infinite. I mean, they're all different. So then, I'll just say then all powers of A are distinct. I mean, actually, let me give you the one-line proof of this, right? So what I'm saying now is that if I try to write down a list of powers, I'll never end, including the negative powers, right? So I've got A to the 1, A to the 2 forever, and I've got A to the 0, A to the minus 1. So these are all distinct, all the powers of A to the minus 1, A to the 0, A to the 1. This is a set of, those are all distinct elements. And, we already saw this with the integers. You take the number 2, its powers are just the multiples of 2, right? 2, 4, 6, 8, 0, minus 2, minus 4, minus 6. Those are all distinct elements. So one-line proof of this, is if you did have A to the I equals A to the J for, say, I bigger than J, let's do the same trick. Divide by A to the J or multiply by A to the minus J. So if I take A to the I minus A to the J, this will be equal to A to the J minus J, which again is E. And look at this, I've got A to a finite number equals E. Contradiction to what we said that A had. The infinite order of A means you cannot find a finite power. So contradiction to the fact that A has infinite order.
You need better chalk.
Do you have some?
Yeah.
Oh, really? Well, I'm about done, but maybe.
Okay.
Well, where were you half an hour ago?
I didn't know it was so tiny.
Oh, yeah, I'm gonna have carpal tunnel at the end of this.
So,
Yeah, we're down. Oh, this one's almost a centimeter long, so this is good.
okay.
But I've got one more thing to say, and then we'll break. But thanks. Okay, so last theorem that you guys are going to prove in your homework is also a very useful thing. So is that clear that infinite order gives you all distinct powers? That's again a useful thing that we'll use. So here's the kind of nice fact. Again, back to the finite order stuff. If the order of an element A is n, then, well, and let's let, and t is an integer, bless you, then A to the t is the identity if and only if, well, t divides n. Sorry, n divides t, n is the order, right? So what does n divide t means that I can write t as a multiple of n, right? So i.e. t equals nq for some integer q. Okay, so if you give me here's this element A, it has an order, a finite order. If you know that A to the t, A to something else is the identity, then something special is about t. It has to be a multiple of n. So that's the homework problem. one direction is very clear, hopefully, and well, I want you guys to. So proof is easy for me. It's homework. Okay, so yeah, let's take a break now, 5 minutes or so.